I hope the PPT is visible at your end. Is it visible at your end? PPTs?
Yes,
Yes, sir.
sir.
Okay, thank you. So, as we have completed 2 units, first unit by me, second unit by Dekika sir. Now I will be completing unit number 3 um, again within 8 to 10 lectures. And here is the brief syllabus of unit number 3. It's completely dependent on stability analysis and root locus technique. And here the first point in this unit is stability analysis, wherein today we'll see the concept of stability, which we already partially have seen in unit number 1, but we have to repeat it here again as it is the main point of the unit. Then this is somewhat new, necessary condition for stability of any system, of course. Then this is one of the technique, root stability criterion. Root Hurwitz is the technique by which we can directly say whether the system is stable or not. And relative stability analysis. This is the part of stability analysis. And another point in this unit is root locus technique, about which introduction, root locus concept, then construction of root locus, then construction rules, stability analysis of system using root locus, concept of dominant closed loop pole pair, root counter, effect of addition of open loop zeros and poles. So this is the short, say, points of the unit number 3. Moving to the content of unit number 3, first is the stability analysis of control system. Okay, what is the stability? We have already seen this. What is the stability? But just we'll repeat the definition. A stability is the most desired property in designing the system. कोई भी system हो, of course, we need stability. Why stability of the system is important? Again, I'll repeat. Is PPT visible at your end? Because this is small videos.
yes, sir.
Yes.
Okay.
Yes, sir.
Okay, thank you. Why stability of the system is important? See the example here. Here, first example, I'll play the video. Okay, I will play the video. Due to highlighter, it was not properly working. You can see this video. Here is one vehicle which is moving on road bumps, and vehicle is not properly stable. It is a funny video, but you can have this say video for understanding stability. As this vehicle is not stable, what happened you can easily see here. Okay. Second thing, in second video, there is an unstable aeroplane. It is not an animation. It is a real video, because the uh, stability problem of this aeroplane, you can see what happened here during the takeoff. I hope the videos are visible. So this is a kind of example of unstable system. Let's move to the points of your syllabus. Here, why is the stability required? It is restricted to linear time invariant system only. A system is stable if system eventually come back to equilibrium state. जो जो भी उसका equilibrium state है, वहां अगर वापस आता है तो it is stable. when the system is subjected to initial condition. A system is unstable if output diverges without bound from its equilibrium state. We'll see the example for this also. When the system is subject to the initial conditions. And a system is marginally stable if the system tends to oscillate about its equilibrium state. When the system is subject to the, again, initial condition. You can see the example here. On a table, a small ball is kept, which is of course stable. If we apply a force, again due to highlighter it is not working, it is animation. Yes, if you apply a force, it will move, but doesn't come to the equilibrium position. You can see there is another example here. A curve is there on which a ball is kept. Later on, we push that ball, it went out, but does not come to equilibrium condition. I'll say the center of this curve is nothing but equilibrium condition. So it doesn't come back to the equilibrium condition. So this is kind of unstable system. And another one is we have a bowl in which the ball is kept. Then it is oscillated like this and it automatically comes to the equilibrium state. It is a kind of, again, stable system. So we'll see another PPT. Of course, the definitions now. A system is said to be stable if its output is under control. Otherwise, it is said to be unstable. A stable system produces bounded output for a given bounded input. It is called BIBO, bounded input, bounded output. Three types again. Absolutely stable system. If the system is stable for all range of the system component value, जितनी भी range है जहाँ पे variation हो रहा है, if it is stable for all range, then it is known as absolutely stable system. If all poles of the transfer function present in the left half of S plane, we have seen what is S plane. This is imaginary axis, real axis, and the poles are present on this left hand side of the S plane, then it is said to be absolutely stable. Then conditionally stable, if system is stable for a certain range of the component values, then it is said or known as conditionally stable system. And then last is a marginally stable. If the system is stable by producing an output signal with constant amplitude and frequency of oscillation for bounded input, then it is called marginally stable. Of course, these are the definitions. We'll see the example of these definitions. Then what is a BIBO system? BIBO stable system. Mathematical form. Let us consider we have a system with R of t is the input, C of t is the output, and the impulse response is G of t shown in the figure. So this is the input, this is the output, and G of t. Of course, यहाँ पे Laplace form दिया है. G of s, G of t is the system. So here the output in S domain for above system is given by C of s is equal to R of s into G of s. We have seen this in unit number 1. But if we work on into the time domain using convolution property, the output in time domain given by, this is convolution, C of t integral of 0 to infinity G of tau into R of t minus tau dt. Now we'll apply one by one condition to understand what is absolutely stable, conditionally stable, and marginally stable. Now here, if R of t is bounded such that R of t, magnitude of R of t is less than equal to m, and m is of course less than infinity, bounded less than infinity, then the magnitude of the output satisfied that magnitude of C of t will be less than equal to m integral of system, that is G of tau d tau. So you can see here, this can be what absolutely integrable with some constant. Therefore, the output is bounded when integral 0 to infinity g of tau d tau is less than infinity. This is the final quote, that is the system is Bibo stable and only if and only if the impulse response of the system is absolutely integrable. We'll have the diagram is some waveforms here to understand what is absolute integration, how it is absolutely stable. So here it is absolutely integrable for this condition. So that's why it is absolutely stable. For an example, we have a transfer function with g of s is equal to this s square plus 7s plus 12 divided by s into s square plus 2s plus 5. The zeros of the system can be obtained. We already have done this in unit number 1. It is not say that much tough. So zeros can be obtained from the numerator. So numerator is kept equal to 0. Then it will be s plus 3 into s plus 4 is equal to 0. So first 0 will be minus 3 pe. Second 0 z2 will be on minus 4. So those are located here. You can see minus 4 and minus 3. Of course on left hand plane or left side plane. The poles of the system can be obtained, of course, by putting denominator equal to 0. So denominator is kept equal to 0. So you can directly write say s is equal to 0. So first pole will be say simple pole, that is p1 is equal to 0, which is kept here on s plane. Then another you can see s square plus 2s plus 5 equal to 0 हम रख सकते हैं. So directly we cannot compute poles of this. So we'll be, of course it is a complex pole. That's why we'll be using the formula which we already used in previous lectures. So P2 is obtained minus 1 plus J2 and P3 is obtained minus 1 minus J2. So it is a complex pole, minus 1 plus minus J2. As it is a minus pole, minus 1, again the real part is minus 1. That's why it will be in, of course, left hand plane. So this is one of the pole minus 1 plus J2. This is another minus 1 minus J2 and its coordinate will provide you minus 1 real part. So here in this system, by finding out the position of the poles, whether it is in left hand side or right hand side, accordingly you may directly comment on the stability of the system. But you can see this is very small example having few terms in numerator and few terms in denominator. It can be easily computed, but there will be say huge transfer function cannot be manually computed. In that case, we will be using some techniques called Raud-Hurwitz criterion, and that would be some easiest mathematical way to find out whether the system is stable or not, how many poles are located in right hand side plane and left hand side plane. That can be easily identified without say huge calculations. Then the general form of the transfer function. General form of the transfer function of the system is like this: g of s is equal to output y of s upon input u of s. So this is the binomial form, polynomial here. So here we already seen, I'll not read that. The denominator of the polynomial ds equal to 0. If we equate this denominator to 0, that is called the characteristic equation of the system, that you know again. The roots of the characteristic equation are known as poles. हम poles denominator से निकालते हैं, आपको पता है वो, of the system. Assuming the poles of the system is distinct, the transfer function can be expressed in the partial form, partial fraction form. अगर distinct रहे हैं उसके system poles, then we write in partial fraction form like a1 upon s minus s1 plus a2 upon s minus s2 plus ak upon s minus sk. We already done this in numericals in first unit. The poles can be real, imaginary or complex, that also you know. So what about a real pole in left hand plane of the S plot. Let us consider one partial fraction term of above equation. Means which equation? This one. We have just considered this ak upon s minus ak. So we have one part here, ak upon s minus sk. If pole sk is a real, say sk is equal to a, you can see here, then the inverse Laplace transform of this term, of course, will be Laplace inverse of ak upon s minus sk will be ak into e raised to power at into u of t. So it is completely dependent on what now? It is completely dependent on position of sk, whether it is in left hand side or right hand side. Of course, if it is less than 0, it will be in left hand side of the plane. If it is greater than 0, it will be in right hand side of the plane. So we'll consider one of the condition. When the pole lies in left hand plane for a less than 0, then what will happen to this equation? It will be ak into e raised to power minus at into u of t. The impulse response dies out after infinite time, indicating the bounded output response. Hence, the system is stable for a is less than 0. You can see a is less than 0. 0 यहाँ पे है. We have to a minus something value, minus 2, minus 4, whatever. And if you compute the c of t response, then it starts from a of k, goes on decreasing exponentially and dies out at certain point. So you can see this area can be easily found out. Means this whatever equation we have, it is absolutely integrable because we can find out the area. Area is also bounded. There is a finite area here, you can see, and आउटपुट इज ऑल्सो बाउंडेड. जैसे कि आउटपुट भी हमारा इंफिनिटी की तरफ नहीं जा रहा है, एरिया इज ऑल्सो नॉट इंफिनिटी, बोथ आर बाउंडेड. दैट्स व्हाई द सिस्टम इज एब्सोल्युटली स्टेबल हियर. लेट्स मूव टू द सेकंड एग्जांपल. लेट अस कंसीडर द सेम एग्जांपल पार्शियल फ्रैक्शन वाला, ak upon s minus sk. Then real pole is a. Inverse Laplace transform is again same, ak into e raised to power at into u of t. When the pole lies in right hand side of the plane, यहाँ पे अगर है, then what happened? A will be greater than 0 and A will be greater than 0. That means e raised to power 80 रहेगा, minus sign रहेगा. The impulse response increases without any bound towards infinity. Impulse response कैसे हो रहा है? यहाँ से AK से start हो रहा है. It will go on increasing as the time goes on increasing, indicating unbounded output. Output bound नहीं हुआ है. Output is going towards infinity. That's why it is unstable. Hence the system is unstable for a greater than 0. So यहाँ पे one point is clear that if your pole is situated in left hand plane, then system is stable. On real axis I am talking about, not till the time I have not commented on imaginary axis. And if the pole is situated in left hand side, right hand side pole, right hand side of the S plane, then it is completely unstable. Now one comment I want to make here, that if I have suppose 50 poles into the system, out of these 50 poles, 49 poles are situated in left hand side of the S plane and only one pole is situated in the right hand side of S plane, then also the system is unstable. There should not be single pole situated right hand side of the imaginary axis. इधर से कुछ भी नहीं रहना चाहिए. एक भी पोल रहा, n number of poles are there suppose, and एक भी पोल इधर रहा, then system is unstable. Moving ahead, there might be a situation when real pole is at origin. अभी तक हमने देखा it is less than 0, greater than 0, but there might be of course possibility that sk, that is a, is at origin that is equal to 0. So when the pole is at origin, the impulse response is bounded and remains constant with infinity, because what happened, e raised to power 0, it becomes 1. So response will be a of k, it will be constant. So you will be getting constant output. So can we say constant output is bounded? Yes, constant output is bounded. Only if it is moving towards infinity, then it is unbounded. So constant output is bounded. But what about the integration? If you try to integrate for over the long period of the time, the integration is unbounded. आगे आगे चलते जाओ. You will not say get the absolute integration, absolute value of integration. Area you cannot find. It is infinite. Area of infinite. Output is finite, but area is infinite. So in this case, indicating a bounded output response, but output is not absolutely integrable, then system is called marginally stable. System is called marginally stable. Please remember this term. If your area is unbounded and output is bounded, then it is marginally stable. दोनों bounded है तो it is a perfect or absolute stable, और unbounded है तो आपको पता ही है that is nothing but unstable, जो हमने ये earlier example में देखा है. Let's come to the complex pole now. Real pole हो गए, एक less than 0, एक greater than 0, a equal to 0, and we commented on the stability, whether it is stable, unstable, or marginally stable. Let us consider one partial fraction term of the complex pole, or for the complex pole. If sk is imaginary, then say sk will be equal to a plus minus jb, ये फॉर्म में है. Then g of s will be ak upon s minus a plus jb, and ak plus ak upon s minus a minus jb. The inverse Laplace transform, if you take for this term, then what happened? It will be ak e raised to power at cos of bt plus phi or theta into e of t. So what about this? Again, complex pole may lies in left hand side or in right hand side. So we'll consider one of the state here, that is in, you can see these two poles are nothing but a plus minus jb lies in left hand side. I'll write here L. So when the poles lies in left hand side, that is a is greater than, sorry, less than 0, then impulse response decreases exponentially to the 0 after finite time, indicating bounded output response, which is absolutely integrable. You can see the response is like this, sinusoidal waveform hai, but it decreases due to e raised to power minus 80 term jo hai, it decreases and gradually it becomes 0. So you can see if you wanted to find out the area of this, it is absolutely integrable and you can find out the area. So area is also finite and output is also finite, that is bounded, we can say. That's why the system is stable. We cannot say this is marginally stable. It is a stable. Both are bounded. Area is also bounded and output is also bounded. Let's have another example. Here A is SK is complex but lies in right hand side pole. Then it will be what? AK e raised to power 80. It will not be minus 80 cos in bracket bt plus theta e of t. So when the pole lies in right half plane, a is greater than 0. The impulse response increases exponentially to infinite time. ये 0 से start होता है, it increases sinusoidal towards infinity, indicating that unbounded output भी bound नहीं है, response to which is not absolutely integrable. ये बढ़ते ही जाएगा, इसका area भी will be unbounded, cannot be absolutely integrable. Then the system is unstable. So you please remember these small terms. If complex pole is in right hand side, then system is unstable. Complex pole in left hand side, then it will be stable. Real pole in left hand side, stable. Real pole in right hand side, unstable. Real pole at origin, marginally stable. Now complex pole at origin. Let us consider partial fraction term for complex pole. If sk is imaginary and say it is a plus minus jb, then this will be equation same, of course, and the inverse Laplace transform is this. But what we did here, when the pole lies on imaginary axis, that is A is equal to 0. Here A value is 0, but there will be minus J and minus JB and plus JB. So in this case, the impulse response continuously oscillate between limits and never die to 0. You'll get a constant frequency and constant amplitude as shown here, sinusoidal waveform, and does not die to 0, indicating the bounded output. Of course output infinity नहीं जा रहा है, ऐसा कहीं पे नहीं गया है कि यहाँ से डायरेक्ट ऊपर चढ़ गया और इट इज इन्फिनिटी और माइनस इन्फिनिटी समथिंग. इट इज इन बिटवीन टू प्रीडिफाइंड लेवल्स. हमने अभी डेफिनेशन में पढ़ा है, इट इज बिटवीन टू प्रीडिफाइंड levels. So output is bounded. But what about area? If you compute, area is not absolutely integrable or not bounded. Therefore, the system is marginally stable for A is equal to 0 of complex pole plus J, B and minus JB. Some forms of the system, whatever we talked till the time, I kept it on single PPT. A system is said to be stable. Definition same. If the output is under control, otherwise it is unstable. A system produces a bounded output for given bounded input, that is Bebo stable call. So you can see here, you can look at this. It is a S plane. This is the left hand side. This is the right hand side. Left hand side में complex pole है. Then there will be response like this. It is a continuous oscillating system and dies to 0 after certain time duration. If there is a real pole at real axis, then there will be a exponential decay will die out after certain time, absolutely integrable in this both the cases. On the other hand, if pole is real but on right hand side, there will be exponential graph moving towards infinity, unbounded output, so unstable. If there is a complex pole in right hand side plane, then there will be signal starting at 0 oscillating and moving towards infinity, unbounded. So again it will be unstable. So this single diagram will let you remember what is the stability, what is the instability. यहाँ पे एक condition नहीं दिया है, that is if the pole is at 0, then there will be sinusoidal waveform with constant amplitude and frequency in finite area. If there is a complex pole with real part is equal to 0 again, there will be sinusoidal waveform with bounded output and unbounded area. So this is say summary of commenting on the stability of the system. If you have any question, you may ask. I'll take a pause of 1 minute. Okay, so as usual, you don't have any questions. So some important forms we'll see again here to understand stability concept in more detail. Now you can see here there is a system G of S, transfer function C of S upon R of S is equal to 1 upon S plus A. This is the transfer function, simple transfer function. Let's R of S is equal to 1 and taking inverse Laplace transform. So after taking inverse Laplace transform, R of S अगर 1 है, so C of S will be equal to 1 by S plus A. Then C of S inverse Laplace transform लेने के बाद it will be C of t will be e raised to power minus at. So your pole lies in left hand side, real pole. Then your system is stable. Response will be like this. ये हमने very first unit में we have seen this in tabulic form कि inverse Laplace or transform or Laplace transform of each function. So that is derived here. We'll go quickly through it. So here the system is stable. Then if g of s is equal to 1 by s, assuming r of s is equal to 1, then inverse Laplace transform will be step input of course u of t. So your pole is located here and it is giving you constant bounded output, but area is not bounded. It will be infinite as we going ahead. So it is marginally stable. 1 by s means marginally stable. 1 upon s plus a is stable. Another is transfer function is 1 upon s plus s minus a. Taking r of s 1 and taking inverse Laplace transform, it will be c of t e raised to power minus at. So it will be moving like this. Pole is located at right hand side. So of course unstable system. I have a repeated pole at origin that we have not yet discussed. That is g of s is equal to c of s upon r of s is 1 upon s square. We may write 1 upon s square means we may write s is equal to 0, s into s is equal to 0. So it will be s is equal to 0. So repeated pole at 0. Let's r is equal to 1. So you can see two poles at origin in the diagram. And if we go for the inverse Laplace transform of 1 upon s square, it will be equal to t. So it is, you can see the response. It is a ramp going towards infinity, a slope going towards infinity. So of course unbounded. So it is unstable. ये दोनों example है for unstable system. Then a transfer function c of s upon r of s is 1 upon s plus a whole square. Let's derive it. R of s is equal to 0 impulse response के लिए. Taking inverse Laplace transform, it will be what? T into e raised to power at. We know how to plot this both the functions. So I have what? दो pole repeated है real axis पे, that is s plus a into s plus a, that is s plus a square. So these are the repeated pole at a. Due to that, what happened? One response is for t. So you have t. T we already derived. T is what? T alone is what? Unstable on previous PPT. T alone is unstable because it is moving towards infinity. But I have another function along with that in multiplication with that, that is e of minus at, which is exponential decay, dies out after certain time. That's why the product of this is like this. It will increase, will remain certain constant. कहाँ कहाँ ऐसे peak भी दिखाया जा सकता है, and again dies out towards 0. So you can see final output. देखो final output, your output is bounded. And if you go for the area, you can of course find out the area of this graph. Area is also absolute, absolutely integrable area and bounded output. Thereby system is stable. यहाँ पे marginally नहीं बोला है. Then another, I have transfer function g of s, that is c of s upon r of s is 1 upon s minus a whole square. Then it will be t into e raised to power at, taking inverse Laplace transform. Your pole, repeated pole S is equal to A, two poles at the same location is in right hand plane, and we already commented on the stability. If it is in right hand plane, then definitely it is unstable. But let's see the diagram. T is of course this one, ramp signal. Then e to the power at is again exponential going towards infinity. Both are going towards infinity. Of course, product will be like this going towards infinity. So you can see here output is unbounded. Output is unbounded. And if output is unbounded, of course, your area is also not absolutely integrable. And output is unbounded, that ultimately means the system is unstable. So system is unstable here. Let's move to the next. What I have now, I have C of S upon R of S is equal to B upon S square plus B square into B. This B दो बार लिए है, numerator and denominator. It just for the sake of adjustment, you can write it like 1 by B constant into B upon S square plus B square. Let's RS is equal to 1 and taking the inverse Laplace transform. ये function हमने देखा है, A upon S square plus A square is nothing but sin 80. We already have seen. यहाँ पे सिर्फ number बदला है. So by doing this adjustment, what you get, the response after taking inverse Laplace transform of this transfer function will be 1 by B into sine of BT. So means your poles are located at imaginary axis, that is minus JB and plus JB likewise. And your output is sinusoidal waveform 1 by B sine BT, constant amplitude, constant frequency. But if you compute the area, area is unbounded. Area is unbounded towards infinity, or infinity can say towards long period of the time. You cannot compute the area. That's why it is a marginally stable system. Let's move to the next. Here is the system transfer function, which is 1 upon S plus A whole square plus B square. Let's RS is equal to 1. Take in inverse Laplace transform. You please remember all the Laplace properties, inverse Laplace and Laplace properties, so that you can easily work out on this into the examination. So C of t will be 1 by B into e raised to power minus at into sine bt. Now यहाँ पे दो signal है, one constant is there 1 by B, then there is e raised to power minus at. We know what is this signal, and sine bt means your e raised to power minus at है, इसका मतलब ये जो form है e raised to power minus at into sine bt, that is nothing but your pole lies in left hand plane and it is an imaginary pole. So plus JB minus JB, whatever may be the value. So what I have e raised to power minus at multiply by sine of BT, और इसका multiplication करने के बाद you will get signal like this. It will be sinusoidal wave, start at say 0 going towards some positive amplitude. Gradually it decreases and it dies out after certain time period T. So again here output is not infinity, means it is bounded. So I will write here B, bounded output. Sorry. And what about the area? If you wanted to compute area, it is absolutely integrable. So you will get area of this signal. So it is a kind of what? Stable system. It is a stable system. Let's move to the next. दिखने को same दिख रहा है, but I am changing the sign. Okay, initially it was plus here. You can see it was plus in previous examples. Now it is minus here. So it is 1 upon S minus A whole square plus B square. R of S is 1. Then taking inverse Laplace of this function, we have 1 by B into e raised to power 80 now, not it is minus sin bt. So e raised to power 80 है, इसका मतलब your, and along with sinusoidal waveform, your imaginary pole lies on right hand plane of the S plot. Definitely unstable, but we'll plot it. So e raised to power 80 is like this exponential signal moving towards infinity. Sine is like, of course, you know what is sinusoidal waveform. And product of this will be, it will start at 0, start oscillating, increasing the amplitude, and it will increase towards infinity. So what about output? Output is unbounded. I will write ub here. Unbounded. Area is also not integrable, not absolutely integrable. So unbounded output, directly you can say it is unstable system. Then absolutely stable system, again review of the previous. If the system is stable for all range of component values, then it is known as absolutely stable system. If all the poles of the transfer function present in left half of S plane, if the input to the system is 0, then output also 0 irrespective of initial condition. ये होगा absolute stable system का, जो हमने definition पहले देखा है. Then we worked on certain transfer functions, we have seen certain diagrams, waveforms, and now I think this concept is clear what is absolutely stable system. Example, if the system has closed loop transfer function C of S upon R of S 10 upon S plus 2 into S plus 4, find out the response of the system to the step input. Now response is C of S, R of S इधर चला जाता है, R of S into 10 divided by S plus 2 into S plus 4. What is step input? Step input means R of S का हमने R of t अगर किया और E of t किया तो step input का it will be 1 by S. So in place of R of S we will write 1 by S. Step input, not impulse. Impulse will be 1, step will be 1 by S. So here putting that value, it will be 10. Modified response means C of S response will be 10 upon S, that is nothing but due to 1 by S, of course, into S plus 2 into S plus 4. Three terms are there, so we will be solving it by partial fraction. So A by S plus B by S plus 2 plus C by S plus 4. Solving by partial fraction, it will be 1.25. Middle step you have to say solve it. I have directly used say final step. We already did this in earlier unit. 1.25 divided by S minus 2.5 divided by S plus 1 S plus 2 plus 1.25 divided by S plus 4. So I got A, B, C value. Putting into the equation, taking inverse Laplace transform. So 1 by S का means 1.25 divided by S. 1 by S का inverse Laplace transform is what? 1. So it will be 1.25 here. Then इसका क्या है? 1 by S plus 2 का it will be e raised to power minus 2t and 2.5 as it is. So it will be 2.5 into e raised to power minus 2t. What about this? It will be 1.25 into e raised to power minus 4t. At t is equal to infinity, we get, अगर मैंने t की वैल्यू infinity अगर डाला है, so these two terms will be 0. I'll erase the ink. क्योंकि हमें इनफाइनाइट का रिस्पॉन्स देखना है स्टेबिलिटी चेक करने के लिए. So if I put t is equal to infinity, this term becomes 0, this term becomes 0, and your C of t, that is a final response, will be equal to 1.25. Can we say it is bounded? Yes, it is a finite value, so it is a bounded. एक example से solve किया है. We have got finite value, therefore the system is absolutely stable system. ऐसे भी देख सकते हैं, indirectly भी हमें पता है poles कहाँ है for this system. Poles है -4 पे और -2 पे. Still it is absolutely stable, direct we can say. So number of pole P1 is -2, P2 is -4. All the poles in left hand side of S-plane, the system is absolutely stable. Hence, with this example, we have seen how to find out the response, and response से कैसे पता चलेगा अगर हम पोल नहीं अगर locate किए तो. Another is unstable system. For the bounded input, if the system provides unbounded output, then we know system is unstable. If any of the pole of the transfer function present in right of S plane, I said n number of poles, suppose 1000 poles are there and only one pole is lying in a only one pole is lying in right hand side, then definitely it is unstable. If input to the system is 0, then output may not return to 0. It is nothing but unstable system. For an example, if the system has closed loop transfer function, ये ट्रांसफर फंक्शन दिया है, एक चेंज किया छोटा सा मैंने यहाँ पे s+2 था तो मैं s-2 कर दिया s+4, और डायरेक्टली अगर कंप्यूट करे तो ये आएगा p1+2 और p2 आएगा -4, एक पोल राइट हैंड साइड में एक पोल लेफ्ट हैंड साइड में, सो सिस्टम इज अनस्टेबल डायरेक्टली यू कैन सी. बट लेट्स हैव the step response. Find out the step response. Step response will be C of S, R of S 10 upon this term. Then R of S is nothing but 1 by S, putting that again by partial fraction. I'll not read it out. So it will be 1.25 divided by S, यहाँ पे plus sign, 0.833 divided by S minus 2 plus 0.416 divided by S plus 4. और इसके बाद क्या करना है हमें, टेकिंग इनवर्स लैप्लास ट्रांसफॉर्म, क्योंकि हमें टाइम डोमेन में ही देखना है सिग्नल क्या है. तो सो इनवर्स लैप्लास ट्रांसफॉर्म लिया है तो C of t will be inverse Laplace transform of 1.25 by S. It will be simply 1.25 here. Then 833 upon S minus 2, इसका inverse Laplace transform it will be 0.833 e raised to power 2t, and 0.416 divided by S plus 4, इसका inverse Laplace हुआ है 0.416 e raised to power minus 4t, and we'll put t is equal to infinity. This term will become 0, but this term will be infinity, means 0.88833 into e raised to power 2t will becomes infinity. So your response is infinite now. And if the response is infinite, of course it is unstable, it is not bounded, it is unbounded, system is unstable. डायरेक्टली अगर पोल प्लस करके देखे तो भी चलेगा, -4 पे है ड्यू टू दिस टर्म एंड +2 पे है ड्यू टू दिस टर्म, एंड one of the pole lies in right hand side, system is unstable. I think few minutes, 5 minutes will conduct. Critically or marginally stable. Critically or marginally stable system. If the system is stable by producing an output signal with constant amplitude and constant frequency, oscillate for bounded input is known as critically or marginally stable. If one or more pole of simple non-repeated root of the transfer function is present or located on axis of S plane, however, there is no pole present in right hand side. This is very important. Right hand side में रहना ही नहीं चाहिए, एक भी रहा तो it is unstable. Output response will be undamped sinusoidal oscillation of the constant amplitude and frequency. So it is critically or marginally stable. Like this, I have location of pole on axis, stable output, but area is not integrable, so it is a stable system. Then of course marginally stable. Then repeated pole on axis, then it will provide you response like this. You can see response of this and this is different. Yes, it is going into positive as well as negative, but due to the repeated pole on the imaginary axis, it will be complete values are in positive direction, but it is bounded. So it is also stable. Area is not integrable, that's why it is marginally or critically stable. And last, you can see it is not a repeated pole. रिपीटेड का मीनिंग एक ही जगह पे अगर डबल पोल रहा तो दैट इज रिपीटेड, बट मोर देन वन पोल on axis will provide you response like this. Still it is marginally stable, but repeated pole, same pole है, suppose plus my say plus j and minus j, ये repeated है, then what will happen to response? It will oscillate and will move towards infinity by the time, and in this case only it is unstable. पहले दो जो है that those are the marginally stable and last one is unstable. So any question from your side? I'll wait for 1 minute, and if no question I'll end the lecture. I have some announcement, please do not say leave the meeting.
Sir, if we have poles at the left hand plane and on origin also, then what will be the system called?
Left hand plane as well as
On
origin.
origin.
So
Yes, sir.
वो दोनों का जो इफेक्ट है, जैसे हमने अर्लियर पीपीटीज में देखा है, you just try to take one example, solve it, and you will get what इनवर्स लैपलास ट्रांसफॉर्म में आपको दो फंक्शन मिलेंगे, जैसे हमने पहले मिला था. It is like this, you will get two functions. Okay, you try it at your end. E raised to power at भी है और sin bt भी है. Okay, you'll get similar way, and later on you will get what is the final system. So origin पे है, इसका मतलब क्या है? It is a sinusoidal waveform. And left hand side में है, इसका मतलब क्या है? Left hand side में है, इसका मतलब it will be e raised to power minus at, is it?
Yes, sir.
Yeah, so it will be kind of sin. This is what this is for complex pole. So whatever response final you will get, accordingly try to compute the signal. Okay, you just work on it. Any other question? If you are not able to solve that, I will provide you the solution. ट्रान्सफर फंक्शन घेऊन बघावं लागतं तसं, मग लगेच सॉल्युशन येतो. ट्रान्सफर फंक्शन घ्यायचं, then go for the step response, go for the inverse Laplace transform. Then inverse Laplace transform में आपको क्या आता है? C of t is equal to, accordingly your signal will be produced. Okay, don't leave the meeting until unless I instruct you to leave the meeting. So if there is no question based on this, in next lecture, this is all about the what stability. I'll go to the home. Concept of
Sir,
stability. Yes. Yes. Yes, please. Somebody has a question.
Sir, hello.
Yes, who is speaking?
Sir, Revati.
Revati, yes. What is the question?
Sir, my question is regarding to last PPT. Sir, जो सेकंड वाला आपने लोकेट बनाया, जैसे अभी आपने बोला कि अगर पोल रिपीट हो रहा है जैसे माइनस जे और जे, तो फिर वो तो, सर उसी रिलेटेड था.
I'll come to the PPT. This you are talking about, right?
Yes, yes. सर जो सेकंड वाला सिस्टम है उसके अंदर जो लोकेशन ऑफ पोल है, तो सर इस जैसे नीचे वाले इसमें रिपीटेड पोल, जैसे आपने बोला कि माइनस जे जे रहा, तो सर उसके ऊपर वाले के लिए हम कैसे एग्जांपल ले सकते हैं?
Examples.
मतलब जैसे अभी आपने इसका बताया माइनस जे जे, तो फिर इसके
like it is a minus j and plus j, and it is a minus 2j and plus 2j. This will be what? This second example. Okay.
Yes,
But
sir.
what is this? This is minus j two times, sorry, plus j two times and minus j two times, or you can say minus 2j two times and plus 2j two times.
ओके।
एक ही जगह पे दो। ये सेकंड एग्जांपल में इमेजिनरी एक्सिस पे पोल्स है, बट अलग अलग जगह पे दो इमेजिनरी एक्सिस है। लाइक व्हाट? लाइक प्लस माइनस 1j एंड प्लस माइनस से 3j, कुछ भी लो, 3j 2j। ये हो गया इसका एग्जांपल। बट सपोज यही दो बार रिपीट है, ये वाला, ये होगा इसका एग्जांपल। एनी ऑफ दिस प्लस माइनस 1j अगर दो बार रिपीट हो रहा है, सो दिस एग्जांपल। और प्लस माइनस वॉट एवर 2j रिपीट हो रहा है दो बार, तो दिस एग्जांपल। एनी अदर क्वेश्चन?
नो सर।
Okay, so I'll end this lecture. Thank you very much. The PPT for this will be uploaded tomorrow. I don't have time today to upload. Again, video will be also uploaded tomorrow. So